Welcome to the Zoom room. I'm Jared Skeens, and we are going to today look at the part 2 of our trigonometric series. And so our trigonometry part 2 today is going to cover degrees and radians. So in part 1, we covered some of the basics. We reviewed Sekolah, we reviewed special triangles, and then we got into an explanation of the unit circle. So what we want to do in part 2 is take a closer look at those special triangles again, and also degrees and radians. In the introduction, we only looked at degrees, so we want to explain radians, and we want to see how both of those units fill out the complete unit circle, and how the special triangles help us in figuring out the degrees and radians more quickly for those special values. So in our part 2, we'll look at degrees first. I think there's 2 reasons why people tend to like degrees better than radians. One is, I think degrees are introduced to us earlier, like maybe in an elementary. We even use it more in our language. For example, if someone says, oh, they made a 180-degree turn in their life, well, it means they turned around and went completely the opposite direction. Or in basketball, a person goes up for a dunk and turns all the way around, and we call it a 360. You don't hear someone say, oh, they made a pi turn in their life, or the person went up for a basketball dunk and did a 2 pi. You don't hear that. So most of our earlier years introduction, even how we talk in language, uses degrees. The second reason why I think people like degrees better than radians is because they're nice whole number values. So you have 0, 90, 180, 270, 360. They're only 2 or 3 digit numbers, and they're whole number values. When you get into the radian system, you're going to get into fractions. You have to be really good at fractions to work with radians. Or if you're not working with the fractions, you can also be working with the decimal equivalents. And so even working with the decimals or fractions is a little difficult for some people. So I think there's generally a preference towards the degree units. However, like I mentioned in the first part of the series, radians is often used, especially by mathematicians and scientists, when you start putting it into formulas, because it's a non-unit unit. It doesn't carry the little unit symbol like degrees does. So if you use degrees in a formula, you have to keep track of that unit. It makes it more difficult when you start applying it, especially in areas of science. So we're going to come back to that and show why is radians a non-unit unit. So, but we're going to start with the degree system. So, what is a degree? Well, basically, someone in the past, I think it was the Babylonians, but I might be wrong on that, somewhere in the past of human history, someone took a circle and divided it into 360 parts. Now, I don't know why it came out to 360, but they divided a circle into 360 parts. So basically, 1 degree is 1 out of 360 parts of the circumference being the distance around the circle. So here we have 2 circles, one with a smaller radius, one with a little bit larger radius. And if you were to take this circle, say you cut it right here and stretched it out into a line, and then you take that length and you cut it up into 360 parts, and you take one of those parts and you put it here on the circle, this the length of it here, and drew a line through it, that would be 1 degree. Now, 1 degree is a little bit difficult to show. So I put on here 30 degrees. So if you took this circle and you cut it and made a length of it, cut it up into 360 parts, and then you took 30 of those parts and laid them out here, they might take up this length approximately right here. I didn't actually measure the 30 degrees, I just put it out here. And so this would be 30 out of the 360 parts. Now notice the next circle's a little bigger. The radius is a little longer, meaning the circumference is larger. So again, if you were to cut it here and you get a longer piece and you cut it up into 360 pieces and take 30 of those, it's bigger than what this one was. But notice it still arrives at the same line. It's still connected, going in the same direction. And so this is the 30-degree direction. So 0 degrees, remember from our introduction, 0 degrees is our reference point. We're standing at the origin facing 0. And so if you rotate 30 degrees, then this is the direction that we would be facing if we took 30 out of 360 pieces of the circumference and put it together. It comes up to facing that direction. So notice I just put circumference. I did not put the formula for circumference. I just put the word circumference. 1 out of 360 pieces of that, 1 piece would be 1 degree. So for every piece of those 360, that's 1 degree of rotation as you go around your circle from 0. 90 pieces out of 360, well, that's 1/4. 180, well, that's halfway. Then 3/4 is 270, all the way back to 360. So you have these nice whole number values, 0, 30, and then you have others like from your special triangles. So you have 30, 45, 60, 90, and then you get your second quadrant angles up to 180, your third quadrant angles down to 270, your fourth quadrant angles from 270 to 360. So this is what a degree is, but notice it is a unit of angular rotation. A unit of angular rotation. So we have to show the unit with a degree symbol. That's the unit, just like centimeters is a unit of length, or degree for Fahrenheit or Celsius, it's a unit of temperature. So the degree in with degrees in trigonometry is a unit of rotational movement, right? So this is the degree system, and generally we're going to come back to this as well. When you are working on a problem in trigonometry, there'll usually be a domain statement. Domain statement tells you the allowed values that you can have in your answer set. So a normal domain would be from 0 to 360, or in other words, a complete circle or all 4 quadrants would be normal, but sometimes they limit it. Instead of a full circle, maybe they only put a half circle, 0 to 180. Or sometimes they do weird things, like maybe you can go from 0 to 90, or you can go from 0 to -90. So they limit it to like first and fourth quadrant. And so it might say -90 to +90. But this is a domain statement telling you the allowed values that you can have in your answer set. So it's important to check this first before you start a problem. We're going to come back to this because this tells you what units you're working in. So this is all that you would find with degrees. Now, when we get over to radians, it's based on a little different idea than an increment of rotation or dividing your, it's not dividing your circumference by a specific number like 360. Instead, if you look down here at your circumference formula you might remember as circumference equals 2 pi r. Circumference equals 2 pi r. So the 2 pi is actually our 360, the complete circle. So when we're looking at our complete circle in radians and we get our complete circle, the 2 pi by itself, we see that radians is actually the circumference divided by the radius. In other words, the length around the circle divided by the length of the radius. So again, if you were to take your circle and cut it at the 0 mark, stretch it out into a line, and then you take the radius of the circle and see how many of those radius lengths will go into the circumference. That's the idea behind radians. So really what 1 radian is one length of the radius along the circumference. So here's the smaller circle, the radius is this long, and so if you take that length and you put it on your circumference, you end up right there. Here's a bigger circle with a bigger radius. If you take that radius length and put it on the circle, you end up here. And notice it's still facing the same direction. So instead of calling this direction by degrees, that is the number of pieces out of 360, this is in radians, or in other words, radius lengths along the circumference. Well, if you notice, 1 radian is a whole lot bigger than 1 degree. In fact, I didn't even put 1 degree on here because it's so small. I put 30 degrees. And even 30 degrees, as you can see, is not as large as 1 radian. So when you use the bridge is what transitions or how you can calculate from one unit into the other. So for example, in the metric to English system, we know that 1 inch is 2.54 centimeters. So that's your bridge. So however many inches, multiply it by 2.54, or however many centimeters, divide it by 2.54, and that's how many inches you have. So you can go back and forth between the two units if you want to. This is the bridge that you cross over to get from one to the other. So the bridge that we use is 180 degrees is equal to pi radians. Now, that's the bridge that we use. So what's this pi? Why isn't it a number? Well, actually, when you lay out these radius lengths, like if I take this one from the short circle, 1 radius, lay it out on the circumference, and then I put a second one, and then I put a third one, I come up just a little short of halfway. So I can get 3 and just a little bit more to get to halfway. If I go all the way around, I can get 6 full ones, and then there's still a little bit more. So what we find out is that you can get 3.14, and the number goes on, radius lengths for a half a circle, and if you do a full circle, it would be 6.28. So for a half a circle, you can get 3 full radius lengths, and then there's just a little bit left. And if you go all the way around, you can get 6, and then there's the 0.28 of a radius length left over. So that's where this number comes from. Well, this number happens to be irrational, meaning the decimals continue on and they don't repeat. I mean, there are numbers that show up again, but it doesn't repeat in a pattern like 1/3, which is 0.3333, or something like that. So it's a non-terminating, non-repeating decimal, which means it's irrational. So instead of having this long decimal number, it has been designated a Greek letter, the Greek letter pi. So just like we use the Greek letter theta to represent the angle rotation, we use the Greek letter pi to represent a half of a circle. Hence, 2 pi represents a full circle. So pi then being 3.142 rounded off here. Now you say, why do you use 3.142? A lot of people, when they think of pi, will say, well, I use 22/7, or I just use 3.14. Why 3.142? Well, remember, our series is specific to the Cambridge curriculum, and the Cambridge curriculum requires most of their answers to be to 3 significant figures. So if your final answer needs to be to 3 significant figures, then that means the numbers you're using in your calculations before the final answer should be taken to 4 digits. That way it guarantees that your 3rd significant figure on the final answer will be accurate. So if you only use 3.14, yeah, some of the time you'll still get the same answer, but there's the possibility that that 3rd value might not come out exact if you only use 3.14. So that's why for Cambridge, they use 3.142. So I think the actual value is like 3.1415 something. And so the 5 rounds up the 1 to a 2. So that 4th value is rounded, but it will guarantee that when you get to your final answer that your 3 significant figures are accurate enough for the Cambridge curriculum. Now, if you use the 22/7, again, it's slightly off. It rounds to 3.143. So again, it is close. It's okay for most practical calculations, but when we're trying to be specific to a curriculum that requires 3 significant figures, the 22/7 rounds out to 3.143, and you just have that potential of occasionally your 3rd digit not being the right number it's supposed to be. So for Cambridge, use 3.142, or better yet, use your calculator, and somewhere in your calculator, you can see the little pi sign right there. And so you can just use the pi value on your calculator, which will give you, of course, all the digits. And you don't really need them all, but since it's in your calculator, you can just use that. So this is the bridge from the degree system into the radian system. So if you use this bridge, you can calculate that 1 radian actually comes out to approximately 57.3. So again, this is the 3 significant figures. And Cambridge, when you're dealing with degrees, you want to go to 1 decimal point. So actually with the trigonometry, when you get an angle value, they don't actually follow the 3 significant figures. They follow the 1 decimal point for an angle measurement. Length measurements, other measurements need to be 3 significant figures. So 57.3 degrees is approximately the value of 1 radian. So notice 1 degree is really small, 30 degrees is up to here. So 57 degrees, well, that's almost 60. That's, up here. And again, I didn't measure this. I just put it in approximately. So this would be approximately 57.3 degrees, or should be, would be 1 radius length. Of course, if you multiply this by 3, you'll get your 180. And if you multiply it by 6, or if you if you multiply it by 3.14, you'll get your 180. If you multiply it by 6.28, you should get your 360. Okay, so a radian is a radius length. Now, why do we call it a non-unit unit? Well, when we go to isolate the pi, it doesn't really matter whether you're isolating the full circle 2 pi, or you can divide the 2 over and just get pi by itself. If you want to calculate the value of pi, you could have the 2 over here. It doesn't really matter which one. In both cases, you have the circumference, which is a length around the circle, divided by the radius, which is also a length. And so let's just say we're using length measurements of centimeter. So if we have a circumference that's in centimeters, and we're dividing it by a radius that's also in centimeters, well, guess what happens? Those units cancel. Centimeters divided by centimeters, they cancel. And so we're just left with a numeric value, like a scalar value. There's no units to it. So the units in radians, because it's circumference divided by radius, or one length divided by another length. That's different from degrees, which is a length just divided up into 360 pieces. So one piece is called 1 degree. You still have the unit. It's just an angular unit. Over here, when we divide length by length, the units cancel. And so that's why sometimes radians is referred to as a non-unit unit, although sometimes you'll still see people write RAD beside it just to identify it as radians. But writing RAD is just so that you can know, looking at it, that it's radians, but you don't actually have to keep track of it in the formula. In fact, I go back, remember I said I wrote the word circumference? I didn't use the formula. Why? Because our formulas that we use, circumference of a circle, 2 pi r, area of a circle, pi r squared. Both of our formulas that we're very familiar with don't use degrees. They use radians. So we've learned radians already. We just maybe not associate what radians are. Maybe we haven't learned how a radian is actually, what it actually is. So circumference equals 2 pi r. I can't put that up here because we're working with degrees, not radians. Can you imagine area? For example, area. You're doing area of a circle, and instead of 2 pi r, you have, say circumference. Circumference, instead of 2 pi r, you have 360 degrees r. But r is in centimeters. So that means our circumference should be what? Degree centimeters? How do you do a degree centimeter? See, it's a little confusing when you start applying it to formula. So we don't do that. Same thing with area. Our area is pi r squared. Can you imagine if we did area as, well, pi is 180 degrees r squared? Well, r again is centimeters. So your units for your area would be degrees centimeters squared. Well, then how do you compare the area of a circle, which is in degrees centimeters squared, with, say, a square, or even a rectangle? Doesn't really matter. We can make it a rectangle. And the area of the rectangle is so many centimeters by so many centimeters. And so our area is going to be centimeters square. Well, how can we compare the area of a rectangle or a triangle, which both are going to be in centimeters square, with a circle if our units is degrees centimeters square? You can't really compare them, the area like that, because the units are different. So that's why in most formula and practical or scientific mathematical calculations, uh, radians are used. The units cancel out. You don't have to worry about keeping track of that extra unit. Notice we don't put radians at the end of 2 pi r. It's just centimeters. Centimeters for the radius, centimeters for the circumference. When you solve for the radians itself, or for how many radiuses are in a half circle or a full circle, those centimeters cancel out, your units are gone. So that's why we refer to radians as the non-unit unit. So we still write radians sometimes we don't. The units cancel, but you don't have to worry about it. And you can compare the area of a circle with areas of other objects that have the length units to it, but they don't have the angular rotation unit. So that is a big advantage of the radian system. Unfortunately, the radians have fractions and decimals. And yes, you can get decimals in your degrees as well. But generally speaking, most of your values like this are whole number values, and you don't have to, you don't have fractions and decimals like that. So like I said, I think that we're introduced to it earlier in our educational development. We use angles a little bit more often in our normal conversation kind of things. But when it comes to mathematical and scientific things, the radians are the preferred way to go. Your Cambridge questions will mix it up. They'll do some questions with degrees, some questions with radians. So you really need to be on your toes and pay attention at the beginning of each question. First, check the domain. Most questions will have a domain statement. So we already looked at the domain statement for degrees, and this would be a domain statement for radians. Notice you do not see the degree symbol. You still see 0 because that's still the positive x-axis. The 0 is your reference point. But instead of 360, you see 2 pi. So if your domain includes a full circle or all 4 quadrants, you'll see 0 to 2 pi. If you only have half a circle, 0 to pi. Again, you can do things like negative pi halves to positive pi halves, just like over here would be 90 and negative 90, pi halves and negative pi halves. So, but check the domain statement so that you know which unit you're dealing with. That should be the first thing you check anytime doing a trigonometric problem. Anytime you plan on using your calculator with the trig function, sine, cosine, or tangent, you must first check the domain statement and identify your units. The reason is because your calculator is doing the work for you. Now, maybe back in previous grade, maybe with circular measurements, you might have learned separate formulas for calculating, say, arc length. And there's one formula that uses degrees. There's a different formula that uses radians. So you chose the appropriate formula based on the unit. Well, now that your calculator is doing it for you, the calculator has to know which formula to use because they're different. So what you need to do is, after you determine which unit is, you need to set the mode on your calculator. So depends on the type of calculator that you have. some calculators have a little mode key right here, and all you do is just keep hitting the mode key, and each time you hit it, it will give you a set of like settings. And usually the first and second settings are not for trigonometry. So you might have to hit it 1, 2, 3 times. I'm not sure how many. I think it's like maybe 3 times, 3 or 4 times. And then you'll see a row saying DEG, RAD, and GRA, or GRAD. So there's degrees, there's radians, and there's even a third one called gradians. But generally speaking, we don't use gradians in junior high and high school. We only use degrees and radians. So you won't have to worry about that third option. But you'll see degrees, radians, gradians, 1, 2, 3, and then you select the number according to the list. Now in this calculator, it doesn't do it that way. Instead, we need to hit the shift button and then the mode button, and you see it gives you this list. And in the list, you can see number 3 degrees, number 4 radians, number 5 gradians. So you don't have to worry about the other things in the list. So you just select the number that you want. So if I want degrees, I select number 3. So when I select number 3, at the very top of the calculator, you can see a little D right there. You have to look really close because it's really small and it's right up in the top of the calculator. You see the little letter D. If you select radians, you'll see a little R up there. So before you start a problem that deals with trigonometry, check the domain and then make sure you're in the right mode. It's sad when a student goes through an entire trigonometric question, actually does everything right as far as procedure, but ends up with the wrong answer because their calculator's in the wrong mode. So be careful of that. Always check the mode on your calculator before. And I have been guilty of that as well. You know, oh, this answer doesn't make sense. Oops, I'm in the wrong mode. So please check the mode, change the setting before you begin the problem. And especially with Cambridge, where each question might change modes, you want to change the mode at the beginning of the problem. You don't want to be halfway through and figured out that you've been doing wrong calculations because your calculator's using the wrong formula. So that's important that you do on that. Okay, so we've talked about the degrees, we've talked about the radians, we've talked about your calculator and making sure that it's in the correct mode. So now what I'm going to do is I'm going to go to screen sharing, where you can see that diagram that I showed you in the introduction, or the part 1 of the series, with the unit circle with all the degrees and radians on it, and help you work through the circle in both degrees and radians, and also see how it relates to the special triangle. So let me just remind you really quick. I'm going to just erase this for now and put up our 2 special triangles. Here's our 30, 60, 90, 1, 2, root 3. Okay, remember that if you want to draw it down somewhere so that you can remember it, because when I go to screen sharing, you won't see this. And here's 45, 45, 90, right triangle. And this is a 1, 1, root 2. So again, if you're trying to remember it, remember in the introduction, I said the 2 is always on the hypotenuse. So this follows a 1, 2, 3, or actually 1, 2, root 3, but it's right in order. 1, 2, root 3 for the 30, 60, 90. The 30 is your smallest one, so it gets the 1 across from it. 30, 1, 2, 3. Although in order of size, the root 3 is 1.7. So 30 is the smallest, then 60, then 90. But it's easier to remember 1, 2, root 3, where the 2 is on the hypotenuse. Same thing with the 45, 45. Since these two are same angles, that means their sides will be the same. So this is the 1 root 2. Again, the 2 is on the hypotenuse. So you only need to remember those two triangles. Okay, that's your special triangles that you need to remember to help you work around your unit circle. Now let me go to screen sharing and let's see what we get here. In the screen sharing, here we see our circle here. So what we have here, you can see our circle. We have on the right-hand side, that is our point of reference. So from the origin, you face the 0. Now notice on the inside are the degrees. Then next are the radians in fraction of pi. Also remember that anything that's radians has pi in it can also be converted to decimal. It's just substituting pi for 3.14. So a lot of times, especially if you're using your calculator and you're working with radians, you're going to get decimal answers. But you can, if you use the pi, you can sometimes get your calculator to change to the pi or the fractional pi value. So in your calculator, you need to use your fraction key. It's the little key over here. You'll see a little like ABC fraction on it, and that can switch back and forth between the fraction value and the decimal value. So on the inside, we have our degrees, then we have our radians, and then out here, this is the exact values from the special triangle. Okay, I guess you can see a little bit, my picture here, you can see these special triangles that I put on the board. Okay, so let's start with what's called the quadrantal angles. Now, the quadrantal angles are the angles between the quadrants. So they don't actually create a triangle. So example, we're facing 0 degrees. Well, if I draw a line out to 0, and then how do I make a line to the nearest x-axis? It is the x-axis. So I just get a straight line. I don't get a triangle. Now, like if I come up here to 30, you can see the cursor there. As I go up to 30, I can bring a line down and make a right triangle with the x-axis. But at 0 degrees, I can't make a triangle. That's a quadrantal angle. So 0 and then 90 and 180 and 270, those are the 4 quadrantal angles. Those are angles in addition to the special triangles that you should be able to do with any trig function without your calculator. So some trig problems in Cambridge specifically say to find the exact value. So you need to use your special triangles and your knowledge of the unit circle to be able to come up with these exact values. Notice the exact values will be some fraction of pi, or they will have radicals in them, these roots. So you can't use your calculator, you can't change them to decimal form. Okay, so let's start with the quadrantal angle 0. If we're facing this direction, remember this is the x-axis, that's your cosine value. So the cosine value does have length. The adjacent value has length, and that's why it's called 1, because it's a unit circle. So cosine of 0 is going to be 1. There's 1 length along the x-axis. But notice there's no y-axis. There's no up and down when you're going straight to the right. So that means your sine, there's not an opposite length there like you would have on your 30. There's no vertical, so you get a 0 for the sine. So sine of 0 is 0. Cosine of 0 is 1. Tangent is the sine divided by the cosine. So 0 divided by 1 is still 0. So tangent of 0 is also 0. Now let's go to 90. 90 is straight up. It's the y-axis value. Notice when you're going straight up, there's no left or right. And if you draw a line back to the x-axis, well, it just comes straight down again. So the quadrantal angles do not create right triangles. They're just straight lines. So you need to remember cosine is x, sine is y. So if we're going straight up, we're not going left or right on the x-axis. So cosine is 0. But sine is going in the positive y-axis direction, so it has the value of 1, again coming from the unit circle. Okay. Then if we go to 180, notice it's going in the negative x-axis direction. So cosine being the x-axis is -1. Sine, there's no vertical motion up or down, so it's a 0. Tangent, oh wait, back here, tangent would be sine divided by cosine. Whoops, we can't divide by 0. So tangent of 90 is going to be undefined. In fact, when you look at the domain of tangent will not have the equal sign when there's a 90 involved, or the 270, because both of those involve dividing by 0. So tangent of 90 is actually undefined. There's no value that we can give to it. Tangent of 180 is 0 divided by -1, sine divided by cosine, and you get 0 again. And when we move down to 270, it's on the negative y-axis. So notice the sine value is a -1 because it's the y-axis. The cosine, again, has no horizontal movement, so it's a 0. And tangent, again, is undefined. So those are the 4 quadrantal angles. You should be able to figure out your sine, cosine, and tangent for each of those. Okay. Now I'm going to move up my computer here a little bit so I can stand up a little better. And I think you can still see, if we need to, these special triangles. So notice, I'll try to maybe get over here a little bit. Notice 30 degrees. Okay, 30 degrees comes up here to this point here. If you draw a right triangle, that means the reference angle from 0 to this line is 30 degrees. So the opposite side would be over here. Well, if you go to 30 degrees on your triangle and go to the opposite, it's 1. Opposite over hypotenuse. Sine of 30 is opposite over hypotenuse, 1/2. Notice the 1/2. That comes from your special triangle. And adjacent over hypotenuse, or the cosine value, is √3/2. That's where this comes from. The adjacent over hypotenuse comes from your special triangle, √3/2. When you move up to the 45, again, the 45 comes up here. When you see on the screen, comes up to this red dot. You can make a right angle with the x-axis. So that means your reference angle is 45 degrees from the 0. So 45 degrees, you come up here, make it your the opposite side here. And so you're coming from the 45. The opposite of a 45, whichever one you pick as your reference, is 1/√2. I say, wait a minute, you just said 1/√2. Well, what happens with 1/√2? Well, you're not allowed to have a radical in the denominator. So we do what's called rationalizing the denominator. You multiply top and bottom by √2, and it ends up being √2/2. And that's what you see on the chart there, √2/2. And notice both the adjacent over hypotenuse and the opposite over hypotenuse are both √2/2, because 45 degrees is the same on both sides. So your sine and cosine values are both the same. Which, by the way, if you wanted the tangent value, you just divide the sine, or the y value, by the x value. Sine divided by cosine. So if you wanted tan of 30, you would just use 1/2 divided by root 3 over 2. This invert and multiply gives you 2 over root 3. Your 2's cancel. You get 1 over root 3, which when you rationalize it becomes root 3 over 3. Okay, so you can even figure out the tangents, even though it's not listed on your circle, you can still figure out the tangent value by dividing sine by cosine, or the y value by the x value. So you can work your way around the chart. Now, how does the special triangles, which you can see in your first quadrant, how does that help you with the second, third, and fourth quadrant? Well, remember again your reference angle. The reference angle is the angle between your line and the nearest x-axis. So if you look over here at the 150, your nearest x-axis is the 180. And the difference between 180 and 150 is 30. So this is a 30-degree reference angle, meaning you can use the 30 degree on your special triangle. The only difference is you have to remember that over here in the second quadrant, cosine is negative. So notice your x values are all negative because the adjacent side is going in the negative direction on the x-axis. But all the y values are positive because it's still going up on the y-axis. So 30 degrees, 150 degrees, which is 30 from 180, 210, which is 30 degrees past 180, still the nearest x-axis, and 330, which is 30 degrees away from 360, 30, 150, 210, and 330 all have 30-degree reference angles, meaning you're going to use the 30 degree as your point of reference on your special triangle. So notice the values are actually the same. Root 3 over 2 and 1/2. Negative root 3 over 2 and 1/2. Negative root 3 over 2, negative 1/2, and root 3 over 2, negative 1/2. The same numbers and radicals, only the sign changes depending on the quadrant and the trig function. So same thing with your 45. A 45 in the first quadrant is also the 135 in the second. 135 from 180, you have a 45-degree reference angle over here in the second quadrant. If you go down to the third quadrant, it's 225 is 45 degrees away from 180. And then the fourth quadrant, you have 315. Again, notice your values are all the same. Root 2 over 2 in all four places. The only difference is whether they're positive or negative, depending on your all students take calculus. Remember that from the first session? All students take calculus. First quadrant, notice all are positive. Second quadrant, the sign is positive, all students. And then take would be your tangent. Remember, tangent is the division of the two. So when you divide a negative by a negative, you end up with positive for tangent. But the sines and the cosines are negative. In the fourth quadrant, all students take calculus. The cosine values are positive. The sine and tangent values would both be negative. So you can see how using your special triangles with degrees, you can come up with exact values. In other words, you're not using your calculator, you're not using decimals, you're using fractions and the radicals to give exact values. So even your quadrantal functions will just be zeros and ones, or the positive and negatives of the ones. Now let's go to the radians. So let's go back here to our quadrantal. So remember, 0 is our reference point. Halfway around the circle, our 180 degrees is pi. In other words, 3.14 radius lengths to get over to here. And then if we go all the way around, we would be back to 2 pi. Now the 2 pi is not stated, it just states the 0. But if we get all the way around, we have 2 pi here at the end. Okay, so if this is 0 and halfway is pi, then a quarter of the way, or I'm sorry, a quarter of the whole circle, which would be halfway to the halfway, or half of the 180 is actually half of the pi. So from 0 to 180, we split that in half, we get pi halves, okay? So this is a fourth of a circle. So you really have to be good with fractions and the denominators especially. So if you can work with the denominators, so like I said, if you split your circle into 4, then that means this is 0/4, okay? 0/4 of 2 pi. This is 1/4 of 2 pi. 1/4 of 2 pi, okay? I don't know if you can see over here. 1/4 of 2 pi. So you get 2/4. 2 pi divided by 4 is pi halves. So it's just that the 2/4 reduced to 1/2, okay? So this is 2 pi, or this is 0, so this is pi halves. So you have half of that, and then pi, which means you have 2/4 of the 2 pi. 2/4 of the 2 pi. I know it probably sounds a little confusing. If you write it out, it doesn't look so bad. 2/4 of 2 pi means you actually have 4 pi over 4, which reduces to just pi. So 1/4 of 2 pi is pi halves. 2/4 of 2 pi is just pi. You might not want to think of it that way. You might want to think of it as just halfway to 180 or halfway to pi. So if you know pi is over here, cut it in half, pi halves. So 1 pi half, 2 pi halves, sorry, up here's 1 pi half, here's 2 pi halves, down here is 3 pi halves, and then 4 pi halves is your 2 pi. So maybe it's easier to think of it that way. 1 pi half is your 90, 2 pi halves, the 2's cancel, gives you pi. 3 pi halves, that's your 270. 4 pi halves, that's your 2 pi. So you really have to be good with fractions, which is probably why a lot of people don't really like the radians. Now, deal with 30 degrees. Well, 30 degrees is a third of 90. So if you take a third of pi halves, you get pi 6. 45 is half of 90. So if you take half of pi halves, you get pi 4s. 60 degrees, well, if 30 is pi 6, then that means 60 is 2 pi 6. But 2 pi 6, or 2/6, reduces to 1/3. So let's go back to 90s. If we go around by 90s, you're going by halves. 1/2, 2 halves, 3 halves, 4 halves. If you go by 45s, you're going by fourths. So 1/4, 2/4, you're 90, 3/4, 4/4, that's your 180, 5/4 is your 225, 6/4 reduces to 3 halves, 7/4 is your 315, and then 8/4 again is your 2 pi. If you're going by 60s, 1/3. So 120 would be 2/3. 180 would be 3/3. Then another 60, 240 is 4/3. Then 300, 5/3. And then to 360, 6/3, which is 2 pi. Okay, so you have by halves, you have by fourths, you have by thirds. I guess I should have done the halves, the thirds, and then the fourths. So the halves is your 90, by thirds is by 60, by fourths is by 45, and by sixths is 30. So here's 1/6, 30. 2/6, same thing as 60, or 2/6 reduces to 1/3. 3/6, there's your 1/2. 4/6, same thing as 2/3. 5/6, well, there you see the 5/6. 6/6, cancels out, leaves you pi. 7/6, there's your 2/10. 8/6 reduces to 4/3. 9/6 reduces to 3/2. 10/6 reduces to 5/3. 11/6, there you see the 11/6 on the 330, and 12/6 is back to the 360. So basically, the fractions that you have to be good at are halves, counting by halves. That's your 90. I don't know, can you see this? Maybe I wrote it too low. Let me get rid of some of this. The fractions that you have to be good at are your halves, that counts by 90s, your thirds is your counting by 60s, your fourths, that's counting by 45s, and sixths, counting by 30s. So your fractions with 2 as your denominator, fractions with 3 as your denominator, fractions with 4, and fractions with 6. If you're good at fractions, and you can just count your way around the circle, then you can figure out all of these exact values for radians. Yes, radians are a little trickier than degrees, but you can do it. Now, if you really struggle with fractions, you can use the bridge. Remember the bridge, pi equals 180? So you can actually convert a radian back to a degree. For example, look at the 60. And if you end up with pi thirds and you don't like fractions, you can say, okay, pi is 180. 180 divided by 3 is 60. And then you can use your special triangle for 60 degrees to figure out your cosine, sine, tangent, like that. Okay, so then don't forget, though, to convert back to radians when you're done in degrees. Make sure you go back over the bridge back to radians. So basically, if you want to use the bridge, again, we said we had pi thirds. So we multiply, pi is 180. So this is in radians. So we multiply pi on the bottom, 180 on top. If we want to get rid of radians, we put radians on the bottom, cancels. 180 divided by 3 is 60, and our units is degrees. If we start with 60 degrees, then when we do our bridge, we put the degrees on the bottom, 180 on the bottom, the pi on top. We want to go to radians, so the degrees cancel. 60 over 180 reduces to 1/3, so you get pi over 3. So you can use your bridge either way. Just take your fraction here that you're using, your conversion fraction, and flip it upside down. The unit you want to get rid of goes on the bottom. The unit you want to go to goes on top. And so you can convert from radians to degrees or degrees to radians. That's one thing that you can do if you really, really, really don't like fractions. Or simply use your calculator. Although your calculator may or may not always give you the exact values for it. So remember, when you're using your trigonometric values, you find your sine, cosine, and tangent. Now mine are wearing off, you can't really see it, but they're right here on the calculator. So sine, cosine, and tangent. Kind of hard to do this backwards in the camera. So sine, cosine, and tangent are right here. So I can hit the sine button, and there you see sine, and then I can type in, right now I'm in degrees, so I can hit 30 degrees, and it gives me 0.5. Notice it gives me decimal. So I need to hit that little fraction key, which is right there, and it changes it to 1/2. Now let's see if it does it with 60. Sine 60, and it gives me 0.866. Again, it gives decimal. If I hit that fraction key, no, it does not change it for me. So I'm stuck. If it asks for exact value of sine of 60 and I use my calculator, it does not give me the right value. Now, let's say I do it in radians. Well, I got to change my mode. So I change my mode to radians. And so now I do sine, instead of 60, I use pi thirds. And I'm going to use my pi key down at the bottom. So I do get my pi and then use the fraction thirds. So now it says sine of pi thirds, and I hit equals, and again, still it gives me the 0.866. What happens if I hit the key? No, it will not give me radicals. It might depend on the calculator. You might be fortunate to have a calculator that will preserve your irrational numbers as roots. If you do, that's great, that's to your advantage. But if you don't have a calculator that preserves that exact value, it only gives you the decimal value, well, you have to be smart with the special triangles and this unit circle. So get used to fractions. It's an important part of your ability to work with trigonometry, but keep this unit circle diagram. If you need to download it from the internet, you can find one on the internet, download it, print it, have it in your notes so that when you're working with trigonometry and you have to have exact values, you can even draw on the side your special triangles so that you have both together in the same diagram, and then you can use your triangles. Remember, you come from the angle of reference. So if it's 30 degrees, you come from the 30-degree angle. If it's 45, you come from the 45. So use that as your reference to determine your opposite, adjacent, hypotenuse, sine, cosine, tangent, and you can figure out all these values exact when you need to. But it's important. If you don't learn that, you're going to really struggle to meet the requirements of the curriculum. So I think we're done for the second part. I did not do the examples for like acute, obtuse, and reflex like I hinted at in the introduction in part one. I'm going to save that and put it together with the next part of the series where I'll talk about inverse functions. So I'll do inverse functions and examples of the acute, obtuse, and reflex angles in the next part 3 of the series. So I hope this helps, and thank you for watching the Zoom room, our second part of the trigonometric function, and I look forward to seeing you again in part 3 of the series.